Okay, so welcome back to this next video in which we are discussing group actions. Okay, right. So we've now gone through the definition of a group action, and we've seen how the definition of a group action actually achieves this association of elements of the group with set permutations of the set A, and how the composition of these associated set permutations is consistent with the composition of the elements of the group within the group composition table. Okay, what I now want to do is discuss something else that achieves the same thing as group actions. So I want to discuss a very related concept to group actions, which is the concept of permutation representations. Okay, so what we're now going to discuss is permutation representations. Okay, so once again I'll remind you of the motivation for what we're trying to achieve. Okay, so we're trying to formalize the notion that you can associate to elements of a group set permutations of a set, and have these associated set permutations be consistent with the group composition law. Okay, and permutation representations is another way of doing it. Okay, if you like, it's sort of like the other side of the same coin as group actions. They are completely and utterly related to one another. So if you have a group action, you can get a permutation representation. If you have a permutation representation, you can go to a group action, basically. They are describing the exact same thing, but they are different mathematical structures. They're different ways of describing the same formalization. Okay, group actions is the one that people more often talk about. However, in my opinion, permutation representations is slightly more intuitive. Okay, so let me then tell you what a permutation representation actually is. Okay, so firstly let's once again just do the setup. So we'll have our group capital G as always, and we'll have our set capital A. Okay, so we're trying to associate the elements of the group capital G with set permutations of the set capital A. Okay, so a permutation representation is going to achieve this, but in a different way to how a group action achieved it. So a permutation representation then is a mapping phi, which is going to map the elements of the group onto elements in another group, which is the symmetric group on the set A. So the first thing that I need to do is talk to you a little bit more about this symmetric group on the set A, because we have seen symmetric groups before, but we've only seen the symmetric groups on the sets of n elements. Okay, we've seen the Sn symmetric groups. This is a generalization of those. Okay, so when I write SA here, where you've got some arbitrary set, capital A down here, this is called the symmetric group on the set A. Now what does this actually consist of? Well, this consists of the set that will contain every single set permutation of this set capital A. Okay, so you stick into this set every single set permutation of the set capital A. Now either you can give each of the set permutations of the set A symbols to represent them and stick those into this set, or you could, if you like, actually imagine sticking in the little pictures of the maps. Okay, so you could imagine having all of the elements of the set A here. Okay, so I'll just draw a little picture, and then all of the elements of the set here, and then you've got some mapping here. So let's say that one goes onto that one, that one goes onto that one, that one goes onto that one. Okay, so you've got an actual picture of the set permutation, and you can imagine the elements then of your symmetric group on the set A as actually being these pictures of the set permutation. Okay, all that matters is that you've got some symbol, and after all, this is a very, very fancy symbol. It's a very complicated symbol, but it is still just a symbol. It's loads of squiggles. Okay, so you could, if you like, imagine the symbols of this set being these actual pictures of the set permutations of the set A. Okay, what's important is that the elements of this group are the set permutations of the set A, and that every single set permutation of the set A is included in this set. Okay, then the composition law defined on this set of symbols is quite simply just the composition that you get from the composition of the set permutations. Okay, so if you're thinking about what an element little x composed with an element little y would be equal to, so little x composed with little y here, that would quite simply mean, firstly do the set permutation that's associated with this symbol here, little y, and then do the set permutation that's associated with this symbol, little x, get the new set permutation that is the composite of those two set permutations, and that is then your answer, basically. Okay, so composition in here just relates directly to the composition of the set permutations. Okay, and this does form a group because, of course, it will be closed under composition, because whenever you compose two set permutations together, you get another set permutation. Okay, it will obey associativity because, of course, we're thinking in terms of mappings, and whenever you compose mappings together, that does obey associativity. That's really where associativity comes from. Okay, we will have the identity element in there because we'll have the identity map, and that will compose with any other set permutation to give that other set permutation back again. And of course we'll also have two-sided inverse elements in here, okay, because if you've got an arbitrary set permutation in here, its inverse map will also be a set permutation. Okay, so this is going to obey the axioms of group theory. Okay, so remember, we are trying to associate elements of our group capital G with set permutations of the set capital A. So this seems incredibly intuitive. We're just going to map the elements of the group onto the set permutation of the set A in this symmetric group on the set A that we want to associate it with. Okay? So that's why I say that permutation representations in a way are far more intuitive, a far more direct way of doing what we were trying to achieve than group actions. Okay, now there's another condition, of course, that this mapping needs to obey, because at the moment, again, this is just saying map the elements of the group onto set permutations in this symmetric group on the set A. Okay, but we want the composition law in our group here to be consistent with the composition of the set permutations, or the other way around if you prefer to view it that way. Okay, and that's the statement that we need the property of homomorphisms to be true. So we need this mapping to be a homomorphism. We need it to be the case that if you take two elements of our group, G1 and G2, that phi of G1 composed with G2, so you compose G1 and G2 together before you leave this group, and then take phi of that, so you take whatever the associated set permutation to G1 composed with G2 is in the symmetric group on the set A. This needs to be the same as phi of G1, okay, so the associated set permutation with G1 in the symmetric group on the set A, composed with phi of G2, okay, where this is composition in the symmetric group on the set A now, okay, which of course just relates to the composition of these two set permutations together. Okay, so again this just says that the composition of the set permutations, which is on this side, is consistent with the composition in the group, which is over here. Okay, now I want to stress this point that I dwelled on at the end of the previous video again, which is that we are generalizing now, and it does not need to be the case that distinct elements in the group are being mapped onto distinct elements in the symmetric group on the set A. Okay, so this mapping doesn't necessarily need to be injective. Okay, so it certainly doesn't need to be surjective, because it doesn't need to be the case that for every element of the group, for every element of the symmetric group on the set A, that you have an element of the group that's being associated with it. So this might just be being mapped onto a subgroup of the symmetric group on the set A. Okay, but in fact it doesn't actually even need to be injective. It doesn't need to be the case that the mapping is one-to-one, that each element in here is getting a distinct element in here that it alone is being mapped onto. It can be the case that elements in here are having to share elements in here, either being mapped onto the same element in the symmetric group on the set A. Okay, and again I'll remind you that if this mapping is injective, if it is the case that each set permutation that you are mapping elements of the group onto only gets one element of the group being mapped onto it, then we call that a faithful permutation representation. Okay, right, so this is a generalization then of what we've seen previously, where we've only ever had one element of the group being associated with a single element of the set permutations of the set A. Okay, so now we can have degeneracy in this way. Okay, so what I would like to now show you is how group actions and permutation representations are completely interchangeable with one another. Okay, so if you have a group action by the group capital G on the set capital A, then you can quite easily use this to construct a permutation representation from the group capital G to the symmetric group on the set A. And if you have a permutation representation mapping the group capital G onto the symmetric group on the set A, you can quite easily use that to construct a group action. So the two are absolutely capturing the exact same thing. You can go between the two. People often use group actions, but permutation representations have this advantage of being the very obvious way of associating elements of the group with set permutations of the set A. Okay, so the first way that we'll go then is we'll go from a group action to a permutation representation, and then we'll show that you can go from a permutation representation to a group action. Okay, so let's start off with a group action then, and we will now try and define a permutation representation from it. Okay, so this should be very easy, because what we've already seen is that if you have a group action, you can associate with every element of the group a set permutation of the set capital A. So quite simply, let's define the permutation representation to map all of the elements of the group onto their associated set permutation in the symmetric group on the set A. Okay, so the way that this is going to work is that we are going to map any element of our group, little g, onto the set permutation that is associated with little g, which previously we called sigma little g. Okay, so that is how I'm going to define my permutation representation. It's going to take any element of the group onto this associated set permutation that we used the group action to define, basically. Okay, so I'll remind you that sigma little g was the mapping which sent any element of the set capital A, so any little a in capital A, onto little g dot little a, and we've already proven that that is indeed a set permutation. Okay, and we know that in fact these set permutations, their composition is consistent with the composition of the elements of the group. Okay, right, so we now need to prove then that this mapping is in fact a homomorphism. Of course, we now know that it is a mapping from the group into the symmetric group on the set A. How can it not be? It is mapping each element of the group onto a set permutation of the set A, so it's perfectly doing that, but we now need to make sure that it is in fact a homomorphism. Okay, so we need to make sure that it obeys this property of homomorphisms. Okay, so we need to make sure that for all little g1 and little g2 that you can pick from the group, that phi of g1 composed with g2 is equal to phi of g1 composed with phi of g2. Okay, so firstly let's take on the left-hand side here. Okay, so this is composition in the group here. Okay, and then we are mapping g1 composed with g2 onto its associated set permutation. So quite simply, this will map g1 composed with g2 onto sigma g1, and I'll drop the composition symbol and just write them next to each other. So this will map us onto sigma g1 g2, like so. Okay, so that's what the left-hand side is going to be. So if I actually put in that this is acting on an element A, just to remind us that it's a function of the set capital A. Okay, so this is the mapping that we'll get then on this side. Now on the other side, what will we then get? Well, what we'll get is phi of g1 composed with phi of g2, where this composition is done in our symmetric group on the set A. And of course we know that composition in the symmetric group on the set A means composition of the associated set permutations. Okay, so of course phi of G1 is just going to be the set permutation associated with the element G1 of the group. Okay, so this answer is here. And phi of G2 is just going to be the set permutation associated with G2, so sigma G2 here. Okay, so that's the answer here. Okay, and then if we compose those two together, the new mapping that we'll get will be sigma G1 of sigma G2 of A. So that's the new mapping that we'll get if we're doing the right-hand side here. Okay, so proving that this is true is equivalent to proving that this is true, basically. But why do we know that that's true? Well, we've already proven that that's true. That is exactly what we wanted to prove up here when we were trying to prove that the composition of these associated set permutations by a group action were actually consistent with the composition of the elements in the group. Okay, so in fact we've already proven that that is the case. Remember, all we did is filled in the definition for what these mappings actually were in terms of the group action, and then this reduced into axiom number 1 of the group action. Okay, so in fact, proving that this is in fact a homomorphism is exactly equivalent to proving that the composition of these associated set permutations to the elements of the group is consistent with the composition law on the group. Okay, which of course is what a homomorphism means, so we should have seen that we'd proven that already in the first place. Okay, so that then is how you can go from having a group action to having a permutation representation. Okay, what I now want to show you is that you can go the other way as well. So you can start off with a permutation representation, a mapping which maps the elements of the group onto the symmetric group on the set A, and you can use this to define a group action, and we need to prove that this group action that I'm going to show you actually obeys the axioms of a group action. Okay, so this time what we're going to start off with then is the permutation representation. Okay, so this is this homomorphism that is mapping all of the elements of the group onto the symmetric group on the set A. And we want to prove that we can use this to define a group action by the group capital G on the set capital A. So quite simply what we need to do is define one of these group action composition tables. Okay, so we'll have all of the elements of the group down here, and we'll have all of the elements of the set capital A up here, and once again I'll colour this in. So we'll have the set once again in red here, okay, and then we'll have the elements of the group here in green. Okay, right, so I need to define what all of the entries in this group action composition table are going to be equal to. So quite simply, for an arbitrary element of the group, little g, okay, so let's say that this is the row corresponding to the arbitrary element of the group, little g, and for an arbitrary element of the set, little a, and let's say this is the column corresponding to the element little a, I need to define what g dot little a is going to be equal to. Okay, and the way I'm going to define this is I'm just going to say that it is phi of little g of little a. Now let me explain exactly what I mean by that. Okay, so phi of little g firstly. Phi of little g, well, the permutation representation here maps all elements of the group onto an element in the symmetric group on the set A. Okay, now the elements in the symmetric group on the set A are set permutations of the set A. Okay, so phi of G is a set permutation of the set A. And now I'm saying act this set permutation on the set A. After all, it is a mapping of the set A onto itself, so it can take any little a and map it onto some other element. So that's what this means. It means the mapping phi of little g, mapping the element little a onto something. Okay, so I'm going to define g dot a to be equal to phi of little g of little a. Okay, right. So what I now need to prove is that this group action composition table that I have indeed defined here, because this will always be an element of the set A, so it's looking hopeful. All of the entries that we've got here will be in the set A, so that first challenge is met, but now I need to prove that it actually obeys the axioms of a group action, and there are only two. Okay, so let's start off with the first one, the more complicated one. So remember, the first action of a group action says that for all little g1 and little g2 that you can pick from the group capital G, and for all little a you can pick from the set A, it needs to be the case that g1 dot g2 dot A is equal to g1 composed with g2 dot A. Okay, so this really says that the group action is consistent with the composition law on the group. Okay, right, so quite simply, let's take two arbitrary elements of the group, little g1 and little g2, and an arbitrary element of the set, capital A, okay, and we'll call that arbitrary element little a, okay, and let's put in the definition that we've just made for what dotting actually means. Okay, so remember that we've just defined g dot a to be equal to phi of little g of little a. Okay, so we're now just going to use this definition and translate this equation in terms of this. Okay, right, so let's start off with the left-hand side here. So let's consider g2 dot a. So we can now replace that with phi of g2. Okay, so the set permutation that the permutation representation will associate with the element of the group little g2, and then we'll act this on the element of the set little a, so phi of little g2 of a, and then g1 dot this answer will mean take this answer and then use the set permutation associated with little g1 on this answer here. Okay, so that is what the left hand side becomes. Okay, it means first do the set permutation that the permutational representation has associated with the element little g2, then do the set permutation that the permutation representation has associated with little g1. Okay, now let's do the right hand side here. Okay, so g1 composed with g2 dot a, well this would of course mean phi of g1 composed with g2 of a. Just by the very definition, we're just taking the element g1 composed with g2 and we're dotting it with a, so we just take the set permutation that's associated with the element g1 composed with g2 and we act that on the element little a here. Okay, so we need these two things to be the same. Okay, but that is exactly what it means for phi to be a homomorphism. Okay, so remember the property of homomorphisms. This says that phi of g1 composed with g2, that set permutation is exactly the same as phi of g1 composed with phi of g2. And remember, composition in the symmetric group on the set A refers to composition of the set permutations. Okay, i.e. it refers to this side. On this side we are composing the set permutation associated with associated with g1 and the set permutation associated with g2. So we're firstly doing the set permutation associated with g2 and then we're doing the set permutation associated with g1. Okay, but this is exactly equal to this because of the fact that phi is a homomorphism. If you like, what you could do is rewrite this like so. You could write this as phi of g1 composed with phi of g2, in brackets like that, of a. Okay, so you've composed these two set permutations here together in the symmetric group on the set A, and you're now acting the answer on the set A. Okay, because of course composition in the symmetric group on the set A just refers to composition of the associated set permutations. Okay, right, so that's why these two sides are equal to one another, because these two things are going to be equal to one another, and just applying the definition of how we've defined the group action in terms of the permutation representation, we can reduce this having to be true to this having to be true, and of course we know that that's going to be true from phi being a homomorphism. Okay, so that's axiom number 1 then of group actions satisfied. Now let's turn our attention to axiom number 2. So axiom number 2 says that the identity element of the group must act on the set A and take all elements of the set A to itself. So E dot A must equal A for all little a is an element of the set capital A. Okay, so how can we prove that that is true? Well, again, we just need to apply the definition of how we've defined the group action. Okay, so E dot A in this case will be phi of E acting on the element A. So phi of E of A. Okay, now what do we know about group homomorphisms? Well, we know that the identity element in the domain group will always be mapped onto the identity element in the codomain group. Okay, so the identity element in our group capital G will be mapped onto the identity element in our symmetric group on the set A. Now, the identity element in our symmetric group on the set A is the identity set permutation of the set A, which will map all the elements of the set onto themselves, which is exactly what we need to be true. So indeed, phi of E here will be the identity set permutation of the set A, and therefore will map all elements of the set capital A onto themselves. So indeed, this will be true. Okay, so axiom number 2 of group actions is satisfied. Okay, so the message that you should take from that is that there are two different ways of capturing this concept that we can associate with elements of the group capital G set permutations of the set capital A. Either you can use group actions or you can use permutation representations, but you can interchange between the two very easily. They are capturing the exact same concept. They are different mathematical ways of capturing the exact same concept. Okay, right. So we'll have a break here, and then in the next video what we'll do is we'll look at some examples then of group actions.